Hi everyone, this is a quick video on the uniform random variables. Now there's two types of uniform random variables. There's the discrete type and the continuous type. In the discrete type of random variable, we have a set of values that are all equally likely, and it's a discrete finite set. In contrast, a continuous uniform random variables has a range of values, and that those values are typically denoted A and B when we're talking about this generally. And any value between A and B is possible. So we have uncountably infinite amount of values between A and B. When we have a continuous random variable, we are dealing with PDFs instead of PMFs. The PDF that we have ends up being this flat function, and the height of this function is proportional to the range of the function that we're looking at. So in this case, looks like a rectangle, and the rectangle has height between A and B. The CDF of a uniform random variable looks a lot like the CDFs we've seen before. When it's below the values in the support, it is at 0. So that is this case over here. When it is above the values of the support, it flattens out at 1. Didn't write 1, but I can over here for just transparency. And then in this case, all of the values have the same probability. So every time you increase a value in the support and go up by a unit, no matter where you are in that support, that rate of change up remains the same. So we have just this linear function here. So that is the middle where we have our support values. And that is u minus a over b minus a. Now this is a named random variable, and it comes up really often, and as such, it has its own little shorthand that we've seen before. Just like our other random variables that are named, that it's typically referring to a family of distributions. So there's tons and tons and tons of different types of continuous uniform random variables that one want to think about or are in the same family. And how we know exactly which uniform random variable we need to pick is determined by the parameters. In this case, there are two, and this is A and B, which we've seen so far. These can be any finite real numbers. And this tells us which uniform random variable we care about, which continuous one. Because this comes up so much, we do have a few shortcuts we can use. So instead of using the general expected value and variance equations all the time, when we have named distributions, we often have quick results or expressions that are just functions of the parameters in order to get the expected value variance quicker because it comes up so often. And in this case, for the uniform, we have expressions for that, which is nice. Now, there is also something called a standard uniform distribution. Standard uniform distribution is just this. It is a uniform distribution between 0 and 1. This one's kind of fun, and it comes up pretty often, but what's fun about it is its PDF is just 1 for all values in the support. So it ends up being a 1 by 1 box is our plot, which is kind of cool. And then our CDF ends up just being a linear line or a straight line from 0, 0 to 1, 1. And that's our CDF before it flattens out at 1 and at 0 when you're going positive direction and the negative direction, respectively. So it's kind of a fun, special version of the standard uniform random variable. Now, one thing we haven't talked about, we've mentioned transformations a little bit in the discrete case, but we can also have transformations in the continuous case. Now, one of the types of transformations we're often interested is called location scale transformations. A location scale transformation looks like the following form. You have a random variable of interest. So in this case for us, it is u. The u I am using is just a uniform random variable between a and b. Now, a location scale transformation has two terms. It has this C term over here, and it has another term D, which is the additive component. Now, the C term has a requirement that C must be greater than 0, and it is referred to as the scale parameter, the scale term. In contrast, the D term can be any real number. It can also be zero. Z can't be zero. And D is referred to as the location parameter. Now, if you have a location scale transformation, just about every random variable can have a location scale transformation, but what makes it particularly interesting for a uniform random variable is no matter which scale and location term we are using to transform this variable, the new variable will still be uniform. Now, this is not a property that all named distributions have, and it's not a property all continuous named distributions have. It's just a handful of distribution families that will have this property, and uniform is one of them. So I'd encourage you to look at this and practice to determine if you can find a generalization for what the new random variable would be, what the new y random variable, what is its uniform distribution parameters. I encourage you to try that on your own. But I do want to show an example of why one is called scale and one is called location. In general, the scale one is called scale because what it really changes is the variability of the random variable. So if I wanted to do the variance of y, I have the definition of y, and I'm going to just plug that in. It is c times u plus d. Now, d is just a constant in this case, and the variance of a constant is just a constant, so we can ignore that. C is also a constant, and it is specifically a positive constant. And what we can remember about that is we have a little shortcut or a property that we learned about where we can pull C out in front and just square it. And we can show mathematically that's the right thing to do, but we can also just remember the property. So this just becomes the variance of U. So location scale transformation, we've had both a C and a D term, but only the C term affected the variability or the scale of the data. In contrast, the expected value, so the expected value of Y. Now, I already know what the definition of Y is, so I'm going to go ahead and plug that in. C times U plus D. Now, D is just a constant, and I can break up the expected values by constants. C is the same thing. We can also pull it out in front, and we don't have to square it, which is nice. So this just becomes C times the expected value of U plus D. Now, the location parameter and the scale parameter are both present here in the expected value of Y, where what's interesting about D is it just shifts it all in a particular direction. Although both are present, D ends up having this shifting property, which is why it's called the location term. So those are some quick, interesting facts about the continuous uniform distribution. I will upload another video about other properties.